So this video is going to be on creating contrasts. Now, the actual creation of or calculation of contrasts, especially in ANOVA, happens to be one of the most neglected topics in biostatistics. Contrasts can be used to make specific comparisons of treatments and test various hypotheses. In general, by setting contrast, it aids with model interpretation and it increases the accuracy of your results in the interpretation of different models. So usually this is when you create contrast for categorical predictors, it's called dummy variables. So when you build a regression model with categorical variables with more than two levels, so for example, you have different temperature gradients, cold, lukewarm, warm, or high, medium, low, something that, again, is more than two levels. R is internally computing some transformation that's able to compute a regression coefficient. And what R is doing is turning your categorical variables into a set of contrasts. And this number of contrasts is the number of level of variables that you have. For example, in the ones that I use, 3 minus 1. So it's almost like your degrees of freedom. Here I'll present 3 ways to set the contrast, and depending on your research question and your variables, one might be more appropriate than the other. So in R, there are at least 3 different functions that can be used to obtain contrast variables for use in something like a regression or a ANOVA. So you have treatment, which is another name for dummy coding. In some examples, you'll see contr.sum, and sum stands for contrast that sum to 0. And a lot of these are used for ANOVA models. Poly is short for polynomial. And then there's other names for different contrasts, such as Helmert. And you can all set all of those by setting an argument in the coding, and we'll do that in a little bit. Okay, so actually I can show you it right here. So you can go to, options, contrast, and run that. So R uses different contrasts for unordered and ordered factors. And right here are shown the default contrast functions, but you can manipulate these again with the coding to change the type of contrast function you want. So you can change treatment to Helmert, or if you haven't ordered and you don't want poly, you can change that. Poly meaning polynomial. All right, so let's get started with some of the data. And we're just going to use this data set that's looking at different race factors. So first I want to actually set it to a factor. And that's what I'm doing here. And there's 2 different ways you can do that. You can either do the is factor or factor function and then get a true or false of whether it is a factor, or you can just set it as .factor function. Or easy way to do it, you can just have the factor function within the linear model function, which saves the step of creating the factor variable in the first place. So basically gives you that. Okay, so the contr, I'm just going to call it contr function, is a little different from a lot of the functions because it's really basically 2 functions, as you can see here from the format. So in most cases, you have a function on both sides of this arrow. On the left side, you'll usually have the contrast function. And then on the right, you'll have the contr dot whatever. So that can be contr.treatment or contr.helmert, whatever contrast you want to use. And for each, you have to actually specify the what's called N, and that's the number of base and contrast. And so you have to always specify that. And the default of the argument is 1, meaning that the first level is used as a reference level. So we'll try this by itself just so you can get an idea of how it works and just to simply show what it is doing. So we'll run this. So here you have 4 levels of treatment or your contrast. And then what it's showing is the comparison of one level versus another. So here we have it set at the default of using level 1 as the base or the reference. So here, by having a 1 here, we're seeing that this is for column 2, it's level 1 versus level 2. For column 3, it's level 1 versus level 3. And for the 4th column, level 1 versus level 4. So you're using coefficients to code for what contrast or what combination you're actually using. So back to looking at this. So you have the contrast function. X represents a factor or a logical variable. And then we're using the default number of contrasts, which in this case is 3. And then you use value to specify what kind of coding you're doing. Okay, so we'll start with running some treatment contrasts. So again, this is going to use the default contrast coding, and that happens to be the coding for treatment, which is another name, again, for dummy coding. So this is the coding that's most familiar to statisticians. Dummy or treatment coding basically consists of creating dichotomous variables where each variable of the categorical variable is contrasted to a specified reference level. So in other words, it compares each level of the categorical variable to a fixed reference level. In the case of the variable race, which is what we're working with here, which has 4 levels, a typical dummy coding scheme would involve specifying a reference level. So let's pick level 1, which again is the default, and then create 3 dichotomous variables where each variable would contrast each of the other levels for level 1. So for example, we can choose race equals 1 as the reference group and compare the mean of variable for each level of race 2, 3, and 4 to the reference level. So we'll do that here. So let's try an actual example. So before considering any analyses, let's look at the mean of the dependent variable for each level of race, and this will help to interpret the output for later analyses. So we can do that by using the tapply function and apply the mean analyses to all of the functions that are coded for here. Okay, so here are the mean outputs, and these come in handy later for creating some of the contrast matrices and such. Okay, so the contrast matrix for a categorical variable with 4 levels. So here it's contr.treatment and then 4. This is the level of contrast you have. So this is what we're making, a contrast matrix for a categorical variable with 4 levels. So let's run that. All right, so here we see an output that's very similar to the one that's actually the same as the one up here. So in case you missed it, the first column, here are the 4 levels. This first column, labeled 2, represents level 1 versus level 2 of race. Now, level 1, I think is, correct me if I'm wrong, this is Hispanic, this is Asian, this is African American, and this is Caucasian. So I don't remember what they were doing with race, but they were playing with race. So anyway, what was I saying? Oh, so column 3 is level 1 versus level 3, and column 4 is level 1 versus level 4. Okay. So then if you wanted to actually see the names of the contrast, and if for some reason I forgot what contrast I was using, you can use the attribute function. And usually that works, but for some reason it's not now. But usually, if you want to see what treatments you're actually using, you can, again, use this attribute function. And when it's deciding to be nice, it will actually work for you. Okay, so assigning the treatment contrast to this race.f attribute that we've created. So there's two ways you can do that. You can either do contrast and then have the data set you're working with specifying for the variable of that data set. And then you can either use the equal sign or the arrow, and then you have your contr.treatment. So again, we've seen this before. It's this function that I showed you up right here. So again, on the left side, you have your contrast function specifying your x and then possibly how many you want to use. And then I actually have it backwards here. So you have this, and then on the opposite side, you have this what we call value, and that's your contr.whatever contrast coding you're using, and then the level of bases. So if you're using 1 as your reference level, you wouldn't have anything specified after that coding, but since we're using 4 levels, you would have it, and typically you're using more than 1 contrast. Okay, so back on track. So you can do either one of those. I'm just going to run the first one here, and then we can actually code for the function. Again, we get our little contrast matrix. Okay, so now we can actually pull up a summary, and most times to get the output to see significance, we use the LM function. So we'll do summary, and then inside or internal of the summary, we'll have the linear model function. Okay, so looking at the output, we see that both level 1 versus level 2, which is this one here, and level 1 versus level 4, they are both significant because they have a p-value that is less than 0.05. So that's easy interpretation. And that's the regression summary. So let's see, am I getting ahead of myself? Yes, I am. Okay, so another way of changing the reference levels is, like, if, for instance, we wanted to change the reference level to the second level of reference so that everything is compared to level 2 rather than to level 1, we can, but maintaining the 4 levels of the factor, we can do that through this coding here by using the base equals. So we'll run that, and then let's compare that output with the previous one. So here you see, so 2 has all these zeros, which means it's set as the reference level, whereas here 1 is the reference level. So in the new matrix that we've created, where we're comparing everything to the reference level of 2, we have in this first column level 2 versus level 1, level 2 versus level 3, and level 2 versus level 1. And then, so here's our little regression function again. So let's interpret that now with the new coding. Okay, so the parameter estimate for the first contrast compares the mean of the dependent variable for levels 1 and 2 yielding 11.517. And that's statistically significant. That's this guy right here. Okay. And then the t-value that's associated with that, this value here. If you were to look in a book and on the t-table, you would find that that t-critical value is larger than, sorry, this t-statistic is larger than the t-critical, which also yields significance. So the results of the second contrast, which compares the means of levels 1 and 3, that's this one here. So that expected difference, if you looked at if you actually took the means, I think it would be 1.7. But that expected difference is not statistically significant. Sorry, that's for this one here. Is not statistically significant. And then for this group here, you do see statistical significance. Okay, so and if you look, you see that this intercept codes for whatever the reference level is. So for here, the intercept is coding for race equals Asian because we have it set at level 2, whereas here, before we reset the summary, so here, and I'll interpret this as well for you. So the reference level, oh, this is where I still had it as 2. But again, if you change it, your intercept is whatever level you're testing it on. So here we don't have the reference level set as 2, so the reference level, this intercept would be race equals Hispanic. Okay, and then here again, your intercept is race equals, what is it, Asian. Okay, so another way to basically do the same thing would be to specify which levels of the factor variable are to be included in the model. And you can just do that by writing whatever your variable is. Here we have it set as race.f because we changed it to factor. And then the double equals, and then whatever levels you want. So here we're saying we want levels 1, 3, and 4, which means that we want the reference level set at whatever one is not included. And here we exclude 2, and that's going to be our reference level. So we can run this. So here we get the same thing as what we saw above. I'm not going to scroll all the way to the top. And then if you wanted, you can do the regression model for that, and you're able to interpret the parameter estimates and p-values from that. Okay, so then there's this other thing. So that's all treatment coding. And then there's this other thing called Helmert coding. So Helmert coding compares each level of a categorical variable to the mean of the subsequent levels. Hence, the first contrast compares to the mean of the dependent variable for level 1 of race with the mean of all the subsequent levels of race, so levels 2, 3, and 4. The subsequent contrast compares the mean of the dependent variable for level 2 of race with the mean of all the subsequent levels of race, only 3 and 4. And then the third compares the mean of the dependent variable for level 3 of race with the mean of the subsequent levels of race, which in that case would be only level 4. So the Helmert what we're going to create is a Helmert for a factor variable with 4 levels. And I'm just going to actually create my own matrix here. And then I'll bring up the matrix so you can see. So the first comparison, which is comparing level 1 with, again, with level 2, 3, and 4. And that's this guy here. And those codes are, here, I'll show you right up here. So those codes are 3/4, negative quarter, negative quarter, negative quarter. And then the second one, which is this one here, that second comparison compares level 2 with levels 3 and 4. So we have 0, 2/3, negative 1/3, negative 1/3 for the coding. And then the third comparison compares level 3 to level 4. And that coding that's assigned is 0, 0, 1/2, and then negative 1/2. So you're showing that that decrease basically in your coding comparisons where your reference level is compared to one less than the subsequent, or sorry, from the one that followed, and then you're only comparing subsequent levels. So let's see if this guy actually works this time. There we go. Okay, so here's the contrast. So you can see that here, which ones that were what I just basically said before. Okay, so we're going to assign the new Helmert coding that I just created to the race.f variable, and we're going to do that with the contrast. Now you can either have the equal sign here or the arrow, both work. Okay, so, and again, this is that familiar function that I was explaining before, where you have your contrast function on the one side and your, basically your value, quote unquote, on the other. And then we can pull up the regression summary to interpret the results. So the contrast estimate for the comparison between level 1 and the remaining levels is calculated by taking, the mean of that dependent variable for level 1 and subtracting the mean of dependent variables for levels 2, 3, and 4. So if we recall from that t_apply function, and that's how you would do it. We go all the way up. So bring this up again. So here you would use the t_apply functions for that. So you would do the 46.45, this guy, minus the 58 plus your 48.2 plus the 54.05 or 06 divided by 3, because you're taking just these subsequent values. And that gives you negative 6.872. Let's remember where I was. Here we go. Which is right here. So that happens to be statistically significant. Yay, we have significance. So, the 0.960, which is statistically significant. Okay, so that's this one here, that's statistically significant. Then for the means of level 1 of race is statistically significant for levels 2 through 4. That's this one. And then for this level, we're calculating the contrast coefficient for the comparison between level 2 and the later values. So you could do the same thing, except this time you would have to subtract that mean for level 3. And I'm not going to scroll. Actually, I can because it's right here. Okay, so for this one, we're only looking at these values. So we're having our reference is level 2. So you have 58 minus, and then the two subsequents, the 48.2 plus 54.0552, and you divide it by 2, and you get 6.872, which is the parameter coefficient for this level right here. And we see that that is also statistically significant. So the contrast comparison, or the contrast estimate for the comparison between level 3 and 4 is different from the mean of the dependent variable for the two levels, and that's going on to this one here. So we do this the same thing, except this one will only be that level 3 minus the mean of level 4, and we get this parameter coefficient of negative 5.86. And we see, based on the p-value, it's also significant. So all of those differences between the reference level and the subsequent levels are significant. So if you wanted to use the actual, there's this contr.Helmert function. That doesn't do the Helmert coding. That does the reverse Helmert coding. So you actually get the inverse of the Helmert. But we'll give that a try. So we're going to do that for 4 levels again. And I'll just quickly blow through it. So again, you get, here you see you get the inverses of what we had above. All right. So then another one that's often used is this thing called user-defined coding, which is really fantastic. So in R, it's possible to use any general kind of coding scheme. So here we can actually create our own coding. Basically, you define the contrast coding that you want. So for this example, we would like to make the following 3 comparisons. So let's say the first one is I want to compare level 1 to level 3. And the second comparison, I want to do level 2 to levels 1 and 4. And then for the third, say I want to compare levels 1 and 2 to levels 3 and 4. So in order to compare level 1 to level 3, we use the contrast coefficients 1, 0, negative 1, 0. Because again, we're comparing level 1 to level 3. So to compare level 2 to levels 1 and 4, we would use the contrast coefficients negative half, 1, 0, negative half, where the 1 represents level 2, and then the 2 negative halves represent levels 1 and level 4. And then finally, to compare levels 1 and 2 with levels 3 and 4, we use the coefficients 1 half, 1 half, negative 1 half, negative 1 half. So, and then all of these have been expressed in terms of cell means. So, for convenience, we'll just assume that the intercept corresponds to the mean of the cells. Okay. So we're going to create our initial contrast matrix, and we're going to include the constant term in that. So I'm going to create this matrix that is called MAT, and again, this has the coding that I explained to you. Okay, so there's our matrix, and then I'm going to solve it. Okay, so now I want to remove that intercept term because again in the matrix I included it, but now I want to include it for the actual regression calculation. So we'll do that. Okay. So the intercept again corresponds to the mean of the cell, or the mean of the cell means as shown earlier. So the coefficient for race.f1 corresponds to the difference in the mean of the variable between groups 3 and group 1. Similarly, the coefficient for race.f2 corresponds corresponds to the difference between group 2 and the mean of group 1 and 4. Oh, sorry, I had to think of the ones that we were doing. So that's how you interpret it. So for here, the difference in the means of group 1 and group 3 is significant. Sorry, is not significant. Whereas the second contrast that we coded for, which was, what was it? I think it was group 2 and the mean of group 1 and 4. That is statistically significant. And then this one where we had group 1 and 2 versus group 3 and 4 is not significant. Okay, so let's do another example. So this is what we're actually taking from a CSV that was created. So here's your 3 levels. You have G, R, Y, and we're going to use those as contrasts, which you can see here. So we're applying the contrast to the predicted factor of F data, and the treatment contrast we're setting by default, and we have 3 levels. So G is set as the reference level, and then your 2. And so when you have, sorry, before I continue, when you have alphabetical, so instead of like numbered contrasts, when you have these, anything that deals with a letter, it's ours default is to do alphabetical, so it will rank them alphabetically, and then the first level that's ranked again alphabetically will automatically be set as your reference. So in this case, G comes first in the alphabet, so it's going to be our reference letter. And then the 2 treatment contrasts that are made are the difference between the mean of R minus G and Y minus R. Sorry, Y minus G. And that's this here. And then again, you would just evaluate this the same way, where this is the means from R minus G, and Y minus G is this one here. And they are both statistically significant. Okay, so then we can create some user-defined contrasts. In other words, again, that's where you define the contrast, and we're going to do that using the contrast function. So here you see something that's similar to what we've done before, except we're using the cbind and combine functions, and we're creating the actual matrix ourselves. Okay. So again, value here, which is this guy, is a numeric matrix, and the columns give the coefficients for the contrast of the levels of X, or whatever the quoted name of the function. So in this instance, that name, that quoted name of a function to compute such matrix would be contrast, and then parentheses predictor. So that gives us this here again, where we're creating those actual contrast coefficients. And then you can compute the regression for that. And again, in order to do that, you have to create this linear model in order to get the summary, the regression summary. And based on the p-values, both of those contrasts are significant. Okay. So again, traditional dummy coding. So I'm going to get into this so I can show you doing the traditional dummy coding and effects coding, and then what needs to be done for ANOVA. ANOVA is kind of a different playing field. So I'm going to generate some of my own random data, which I've done here. So I'm going to create my, basically my conditions or my control group. And those are A, B, C, and then control. And then my doses, create the data, and then I'll bring up the string. So everything is factors except for Y. And again, by default, R uses traditional dummy coding or treatment contrasts for any non-ordered factors, and which again I showed you before when I did the what was it called? The options contrast. So you see the default. So for non-ordered factors, it was treatment contrast. For ordered factors, the default is the polynomial contrast. So that works out well if you intend to look at regression coefficients with the LM function, which we've been doing previously. And it automatically sets up, so here we'll go down to it right here and create some nice box plots. This can go away and this can go away. Reset our margins. So it's nice when you have using those kind of functions when you are using, again, your linear model or you're using a regression coefficient to kind of interpret the results, which we're doing here. So here it automatically uses the first level as a reference group. So again, it does that rank alphabetically. So in this case, it uses control A. In some cases, there's another level that you would prefer to use as a reference group. So for example, in this data, the control condition would probably be better to use as a reference than condition A. So you can change the reference group with the re-level function. So here's the levels here. And then we can use the re-level function here and set ref equals, this is meaning reference, so we can set the reference level to whichever we want. Here we want it to be set at control. So we're going to change that around. And then, so that basically allows you, so as you can see, the levels are changed so that they're not in alphabetical order anymore. So you're basically reordering the levels and then changing that reference level to control rather than control A, or sorry, control rather than control A. So notice that those levels haven't changed. So then we'll run our model. And again, we're using the LM function for that. So now the control, again, is being set or being used as the reference group since it's now the first level. So we saved that and we made it into its own data frame, which means, and that's what I did right up here. I kind of, sorry, right here and right here, I created its own data frame. So that way, every time I use that variable from now on for models or for plotting, the order of the levels will be made with control first. So it's also to re-level just inside the model without saving to data frame. So if I wanted to create or use condition C as the reference group for this model, I don't want to use that, or I don't want to save that new ordering to the data frame. I just want to see condition C. So I could just do this right here to interpret the outputs. So the reference level is changed to C. And again, you can see that those levels have been changed. Okay. So note that traditional dummy coding is fine for regression coefficients, but since traditional dummy codes aren't orthogonal, it messes up when you are just trying to partition variance. So first thing that comes to mind when I say that is an ANOVA. So also remember that the default R ANOVA functions use type 1 sum of squares, which is generally not what you want in this case. You want to get the type 3 sum of squares. So you can use the actual ANOVA function from the car package to do that, and then you set the type to 3, as I've done here. So you're going to do a factorial ANOVA, going to load the car package, and then you can run the model, you making sure that you're using the type 3 sum of squares, which is the correct type that you want to be using for this case. Okay, so let's actually set up a proper one for ANOVA. So for an ANOVA, you should set your factors to use effects coding rather than relying on the default treatment codes. And you can do this with the contr.sum function. And this overrides the default contrast and tells it to use the contr.sum function to make the contrast instead. So that's this guy right here. So the contr.sum function, this contrast function gives orthogonal contrast, where you can compare every level to the overall mean. So we'll run these. These are conditions. Here's our doses. Create the linear model, and then note, again, we're setting it as a type 3 ANOVA to interpret the sum of squares. And then you can interpret your output from that. And in this case, you have significance in your conditions and your dose, but not the two of them together. Okay, so what if you have some actual comparisons that you'd like to run? For example, maybe you want to run Helmert contrast on the conditions data, and say you want to run a polynomial trend contrast on dose, this guy here. So as long as they're orthogonal, they'll work fine in an ANOVA. So you can actually do that, which I've done here. So say we want to interpret the conditions with contr Helmert and our dose with contr polynomial. Whoa, that's not what I want to do. Okay. So we can actually do that by using this coding, which is kind of nifty. And then again, you're going to use your linear model or the linear model function to code for the regression. And then ANOVA output to interpret the summary, the ANOVA function to interpret the output, making sure you set the type to 3. And that's crucial that you do that. So again, you could choose to alter the contrast in the data frame itself, as I did above, or you could specify it just within the model call. And you can see that the above contrasts have been saved to the data frame based on these outputs here. So moral of the story, for ANOVAs, effect coding works great. Orthogonal contrast coding works great. Dummy coding, not so much. And when you're doing the ANOVAs, you need to have type 3 set. So you can view the results of all the stuff that we did above. So you do the ANOVA function. It won't show you the individual contrast results. It'll just show you the overall effect of each factor. To see the actual results of each contrast, you're going to use the summary function for the model object. So our object here is model 4, and then you can interpret the outputs from there. You get a couple with significance. So here's your conditions, your dose, and then comparing the condition for the dose, and you can actually see which one is which is nice and easy for interpretation. So those are contrasts and setting up dummy variables.